This is a picture I often present to these days. We have a very big challenge in ensuring that we don't have too high an increase in global temperature. So the Paris agreement that we will not reach more than 1.5 degrees is the purple, and unfortunately the orange is the commitments that the countries have made. So there's really far to go. And how have we been doing in Denmark? Well, in Denmark, as you can see, the blue line illustrates that on the energy sector we've been decreasing emissions. Also, we've been decreasing in here what we call other. But basically what I want to show is that the problem in the future may be within transport and agriculture, where we haven't really seen a decrease. When we look into the future, how are we expecting to produce our electricity? This is an example from our group's homepage, where we are showing an analysis of the energy agreement in the time model. And what we can see is a lot of wind and also quite a lot of photovoltaics, i.e. variable renewable energy sources that we need to find out how to use. Recently, we've seen quite an import in renewable energy sources, as you can see with orange. That is mainly wood. And this, we have to ask ourselves, is this a sustainable way to go forward? Can we ensure that the wood we are importing keeps on being sustainable also in the future, when other people will get the idea to use wood for their own purposes in their countries? Then turning towards the costs, we have many different studies have shown that the cost of going towards 100% renewable energy systems is not dramatically higher than the alternative costs if we don't do it. And also, actually, if we take health impacts into account, it may even be a cheaper solution. But let's just look at the raw costs. What we expect is that in the future, we will see quite an increase in the costs in the transport sector. We will see a decrease in the cost of import, but then an increase in the remaining sectors. So transport really starting to take up quite a lot of the costs in the future. I want to highlight a trend that has happened in the different sectors. First, we went decentral with electricity production. What you can see here is the change from 1985 to 2015, where we see a much more decentral production. Today, we have more than 50% produced with decentral plants, and we have a world record in wind power production with more than 40% in 2017 supplied by wind. If we look at district heating, then we see a similar trend. There's also a very decentral production. More than 50% are produced in decentral plants. And we have another world record. More than 60% of our households are fueled by district heating. Now turning towards gas, which we've started to look more and more at lately, we see more and more biogas plants coming into the picture. And we had another world record in July 2018. We had 19% of the gas in the system supplied by biogas plants. So in this sense, also a place where Denmark is different than many places. What Inaugural is expecting is that we go from the black central production in the North Sea towards the dark blue renewable energy gases, and in a transition phase, import of gas. But we are expecting somehow a decrease in the gas consumption moving forward. But I think it's important to say that as the transition has been in the electricity sector and the district heating sector, so are we seeing now a change in the gas sector. In order to integrate these variable renewable energy sources, we require flexibility. This picture illustrates with the dark blue the production of wind 1 week in 2015, and with the light blue you see the consumption. And what we clearly see is that production does not match consumption, and we want to have more flexibility in the system in order to manage that. we have different options of providing flexibility. So we can have flexible power production, we can have flexible power consumption, we can have storage or import or export of energy. And the different sectors provide in different manners on these aspects. So the power sector, district heating, the gas sector can provide quite a lot on these terms. And then liquid fuels and electric vehicles can also provide flexibility on some of these issues. And if we dive into storages, we can see that we have in Denmark a huge potential for storing gas, storing energy in the term of gas. That's the yellow box, and you can see the black box is what we expect of interconnectors in 2035. And then with district heating, we also have quite a potential in the orange boxes. So we do have some potentials already in the system. Now let me take you on a trip of what I've been working with for the last 12 years. Starting by looking at renewable energy and particularly waste, I have been looking at how to convert this into some useful energy, so district heating and electricity, and this has, for example, been in the Top Waste project that I was heading. Later, I've dived more into district heating in the 4th generation district heating project led by Aalborg University, and in the Progress Heat project, which was a European project we recently finished. There we've been looking at the possibility of heat pumps to provide district heating cheaply and by integrating cheap electricity. Later, I was also looking at how can we convert biomass and waste in biorefineries to feed the transport sector, and this has, for example, happened in the Comets project. And I've been looking at how can we trade electricity, what is the capacity of transmission we need, for example, in the Nordic ETP study done together with the IEA. And then lately we've been looking into storages and also into gas and production of renewable gas in the Future Gas project. So these are some examples of what have been my focus when we are analyzing the full energy system. When I came to Risø, a lot of brilliant people were already studying wind power, so that wasn't really where the extra help was needed, so this is where I went. So how have I been working with this? Basically, you can say I've been doing scenario analysis, applying energy system analysis models, facilitating a dialogue about possible future pathways. So the challenges I was showing you before is that we need to integrate variable renewable energy across energy sectors. We have limited sustainable biomass available, and we need to produce fuel for heavy long-distance transport in biorefineries. So the model development that was required is to improve the modeling of flexibility in integrated energy systems, also modeling the local biomass resources and transportation costs, and modeling biorefineries in a better way. So let's start with the scenarios. I like to see them as a set of organized ways for us to dream effectively about our own future. And what they do is they make a dialogue possible. So in Denmark, we have around 40 years of active energy planning, and we've been providing these scenario analysis. A lot have come from the government, but also a lot have come from NGOs or from universities, thereby facilitating this dialogue. Where should we go? So do renewable energy scenarios have any influence? Well, lately we've seen a lot of different analyses illustrating that we can go to 100% renewable energy in a Danish context, actually without considerable extra costs compared to a business-as-usual alternative. And I was very happy the day that it was announced that there was a political target in Denmark to go towards 100% renewable energy in 2050. That was pretty much a milestone in my career. And I think that all these different analyses that showed that it didn't have to be excessively expensive to go there really helped the politicians dare to make this target. So, moving towards how am I working with these energy system scenarios? I do energy system analysis, and I like to see it as a way of combining inputs from all the different brilliant researchers I have around me. So here at DTU, of course, we have a lot of different departments focusing on technology development, and I have the pleasure of working with some of these wonderful technology optimists and trying to integrate their technologies into these energy systems and showing what could the potential be of these different technologies. We also work with operation research colleagues, helping us improve the modeling. We work with our fellow economists in the division, and also, for example, with the life cycle assessment people. So we try to integrate these different disciplines into, and we try to combine it in the energy system analysis. And the model I've been mainly working with is Balmoral. It's a model which has been applied at a global scale, but that's not the reason why I chose to work with it. I chose to work with it because it was a model that had a good representation of the electricity system and the district heating system, partly in Denmark, but also internationally. It furthermore has the benefit that it can optimize not only operation, but also investments, both in plants and in transmission between these different electricity regions you can, for example, see here. So what really constitutes such a model, and what is it all about? Well, we can talk about the inputs that we need to the model. These are demands, they are efficiencies and costs, and it's also the hourly distribution of demands and potential production from renewable sources. On the output side, what we are optimizing is we are finding which fuels are we using to produce which types of energy where in this system. The way it works is that we often use it as a linear programming tool, but it can be used as a mixed integer programming tool. For example, when we want to optimize economy of scale, and I'll come a bit back to that, or not optimize, but take it into account. So that means big plants are cheaper per capacity than small plants. We also can use it either with myopic investments or rolling horizon. Myopic investments being we just take 1 year and we optimize for that year and we are blind to all the other years around it. Rolling horizon meaning I have an idea what's going to happen 5 years into the future, so I do my investment and then I have an idea for the next 5 years, and that way I also reach 2050. This is how we normally run Balmoral these days. Then there are some very important assumptions in this model, and this is why some people love to hate it. Well, what's that? It is, we are assuming economic rationality, we are assuming perfect markets, and we are also assuming normally perfect foresight within a year. That means I know when the wind is going to blow, and I also know when people are going to have their electricity demand, and that's really smart, because then I can make a super optimal system. Also, you know, economic rationality and perfect markets are questionable assumptions. However, this is not the final answer of how is the world going to develop. What this is the first point to put on the table for a discussion to start. This is where we say this could be possible from an economic and from a technical viewpoint. And then, of course, there are human barriers to make that happen, for example. So putting one equation on the board today, this is the objective function that we try to minimize. We try to minimize the costs. This could be fuel costs, operation and maintenance costs, investments, or costs within transmission. And this is if we run it in a socio-economical optimization. If we want to include private economic optimization, we can add taxes, for example, on fuel or on emissions or any other taxes or subsidies. So, we furthermore have a lot of constraints in the model. We can summarize these into balance equations, which could be for electricity. We have capacity constraints, for example, on power plants. We have energy constraints. For example, we need to use the waste that we produce within a year. And then we have operational constraints, for example, the loading rates for storages. Then I told you that we had the challenge. We wanted to expand in understanding the local use of biomass, the transport costs related to that, and also how do we really integrate these biorefineries, and what are the different types of biomass that we can integrate into them, and how can they produce. And I just forgot a figure here, actually, because down in the corner we have a plant. Normally in Balmoral we have one input. This could be biomass producing two different inputs. This could be electricity and heat. And now that we're going for OptiFlow, which was the model we developed in order to take into account these biomass, local biomass, what we can then facilitate is we can have multiple different biomasses going into a plant and multiple different outputs. This could be also fuels together with electricity and heat, or also fertilizers. The additional inputs we need is a detailed spatial distribution of local biomass resources, heating demands, excess heat sources, also possible transportation routes, the costs, and so on. And then what we get out is how much biomass are we really using from where, and how is it transported. So what we add on the objective function is then the cost of transport and also flow constraints, for example, moving from area A to area B. And the spatial resolution, then we're now hard linking Balmoral and OptiFlow. The spatial resolution in Balmoral is that it's looking at Denmark and the surrounding countries with electricity regions. And in OptiFlow then we are having 36 different district heating areas and 98 municipalities we can drive biomass between. We have an overview of the resource potentials. Here's the manure potential in total, 38 million tons, mainly positioned in the west of the country, and straw potential around 55 petajoules we've used here, and mainly maybe in the east of the country. So now this was the methodology and the challenges, and now let's dive into the fun stuff, which is what can we really then use this for, and let's have some results. And the first example is on import of waste. This is a study I've done with my PhD student, Amalia Pizarro, and also some colleagues from the Southern Danish University, and Chalmers, and then Hans Ravn. First of all, we looked at the economic value and then at the climate footprint of importing waste. So what we saw was that there has been a huge increase in the import of waste to Denmark, mainly from United Kingdom and Ireland, more than 300,000 tons. And we were asking ourselves, is there a raw socio-economic benefit of doing this also in the future? And is there a climate benefit of doing it? So two different questions. And when I say raw socio-economic benefit, I mean we are only looking at the costs, the pure costs. We're not taking externalities into account. So the only externality we take into account is then in the second study where we look at the climate benefit. The way that we've used these two models together is that for OptiFlow we've optimized the transport of waste, and then we've optimized the use of waste to energy. Then Balmoral has handled the rest of the energy production, let's say energy conversion, and in the surrounding countries and in Denmark. We started by looking at how much waste will be available in 2035. And this is a strange picture because 2035, if we look at economic growth, then the amount of waste will increase. But when we then add the recycling targets, we're actually just ending with having the same amount of waste for energy purposes as we have today. That's really upsetting, but that's the best analysis we could do based on the models we have available and how we've seen the historical development. So I'm really sorry. At the moment, it looks very difficult to achieve zero waste, which means having the same amount of waste then that we will have today. I hope somebody will do something about minimization and recycling of waste, but so far, not that much. Yeah, We've looked into two different scenarios for the future. One we call the low elec scenario because it doesn't have so high electricity consumption. It's actually based on the Danish Energy Agency biomass scenario, where we allow some import of biomass, and then a high electricity scenario, which equals the Danish Energy Agency wind scenario, more or less. These two scenarios are both net zero scenarios, accepting the waste. This is always the case. We can go zero carbon emissions, but it's very difficult to get rid of the fossil in the waste. And what we see is a lot of wind and some biomass in the electricity sector, and with the light, the pink is the heat pumps, and then we also have some, of course, the dark red is waste, and we also have some biomass in the heating sector. Now, results. This is our best estimate of the optimal waste incineration capacity in towards 2035. And what we see with the dark purple is the existing plants. With the blue, we see new central plants. And with the light blue over there, we see a little bit of the medium-sized plants. And then we see some plants being mothballed, meaning they're not actually decommissioned because of age. They're maybe mothballed because they're not that effective. So the difference between the low elec and the high elec scenario is mainly that we are mothballing more in the low elec scenario, and we have more central units, and in the high elec scenario we have a little bit of decentralized units also. Showing you on a map, we see a centralization happening in the future. Apparently, we can utilize the heat better, and it's not that expensive to transport the waste around. And then to the original question, do we have a value of importing waste? What we ask ourselves is, if somebody comes to my harbor and gives me waste for free, then is it positive for me or not? As you can see, it's actually positive to import waste. This is today. What we have looked at two different types of waste, a high value waste and a low value waste. And we can see that it's feasible to import up to 250,000 tons of a low value waste and up to 400,000 tons of a high value waste. And the circle shows where we were in 2015. So it doesn't really look that crazy today. It's not a bad business for Denmark. Looking into the future then, will it keep on being a good business? Well, if we look at the development over the years, then yes, there is a positive value, particularly if we're importing a high value waste into a low elec scenario. And if we look at the amounts, we can see we actually have a positive value of importing up to 3 million tons per year, even in the worst case where we have a low value waste in the high elec scenario. So, but what we also see is that the value decreases heavily the more we import. So, a conclusion is that waste incineration, first of all, seems to be moving towards centralized combined heat and power. This is, however, sensitive to electricity prices. So with other electricity prices, we may see that we go more for heat-only plants. It has a positive socioeconomic value to import waste also in the future. Imported waste would have a higher value in the low elec scenario as it displaces more expensive district heating generation, and the feasibility from import of waste will highly depend on the price for wood pellets, because wood pellets is one of the competing technologies to provide the same energy services. And I'll come a bit back to that when we are looking at the biomass, because biomass is a competitor to waste in the Danish energy system. So if I have to answer the question, is there a raw socio-economic benefit of importing combustible waste to Denmark today, in the future? Yes, there is. But you have to make sure that there may not be a good idea to import a lot if you are planning for a high elect scenario. And also you should plan for other heat generation in decentralized district heating grids. Now the next question, is it also a good idea from an environmental perspective? And we can't wait for the answer for that, right? No, this is a bit a complicated picture, but let me take you through it. So what we have is combustible waste abroad. We can prepare it and bale it, and we can transport it by ship or road, and then we can use it for heat only or for cogeneration to provide electricity and heat, and then we're displacing something else in Denmark. We would be producing that energy, we would be producing that electricity or heat in another way in Denmark if we didn't use waste for it. And then abroad, if we don't take it to Denmark, what would happen with it? It could either go to a sanitary landfill with medium landfill gas recovery and be flared. It could go to an engineered landfill with a high landfill gas recovery, go into a gas engine and produce electricity, or we could burn it for electricity only. We are assuming that it does not make sense to export waste from a place where you have district heating and you have waste incineration already. So these are the options we're looking at. And of course, the electricity that you would be producing would have to be produced in another way if you didn't burn the waste. And we're looking into that. So for the district heating and electricity production in Denmark, we're using our energy system models to identify what are we displacing. And abroad, we don't have that pleasure, but we will look into different scenarios. Could be more or less carbon-intensive scenarios. So coming to scenarios, this is the amount of scenarios we looked at. I say we, Cyprian is actually in the audience, Amalia is in Mexico, but Hansen's here as well. So what we looked at was the Danish energy system and the waste quality. That's what I've been talking about the last 10 minutes, so you get that. Those 4 scenarios. Then furthermore, we're looking at different transport modes, different transport distances from 500 to 2,000 kilometers away, different alternatives to waste management, and different alternative electricity production abroad, 5 different scenarios, and then the biomass marginal. So as I told you, we may displace some biomass in Denmark if we import more waste into Denmark. That biomass can be more or less sustainable, and that's what we've been looking at. So all in all, 450 times 4 scenarios. Doesn't look like too much. Eh? I didn't do it, Cyprian did. Okay, so is it a good idea from a climate perspective to import waste to Denmark today? Well, all the red dots below the line says yes. There's 1 dot above the line, so that is the one scenario in which we can say, no, in that scenario it doesn't look too good, because if we burn waste abroad and we displace some electricity produced on coal, then it's better just to leave the waste there, then it does good use there. In all the other cases, it's actually a good idea today to import the waste to Denmark. And when we look at kind of importing, this was now importing 300,000 tons. If we look at importing varying amounts, then we can see that, of course, everything below is positive. So the more we import, the less benefit we have of it. And again, we see that the only place where it's not a good idea is if we incinerate and produce electricity, and that electricity would otherwise be produced from coal. The span illustrates, it goes from driving by truck for 2,000 kilometers or transporting by ship for 500 kilometers. So it's kind of best worst case also on the transport side. Okay, this now is the confusing slide in my presentation. And what you need to see is that the benefit is when we are within the red circle. So this is the good stuff. And all outside is the bad stuff. So what we see is these blue dots from sanitary landfill. So if we import waste, which would otherwise be put on a sanitary landfill, then yes, good idea, let's import waste also in the future. But if we say that that sanitary landfill actually captures some biogenic carbon and keeps it there more than 100 years, then it's kind of not that good an idea. You can see the blue, it's kind of hitting the red line. And similarly, if we have an engineered landfill where we use the gas to produce electricity, then it's also kind of dubious if we are not accounting for the biogenic carbon in the sink in the landfill. So, but in some instances, we can see there's actually a bit of cases where we have a positive benefit. And if we focus on those cases, those are the cases where we have a mixed marginal in high demand. That's the biomass marginal, which is the worst biomass marginal. So everybody is using biomass and we just have the non-sustainable biomass left, and we are displacing that in Denmark, then it might still be a good idea to import to Denmark. Finally, if we look at an engineered landfill where we take into account that carbon is stored in the landfill, that is under all circumstances the best idea. And then we have a few situations where if we incinerate electricity only, it actually also becomes positive. That's the purple dots. And what you see is that if we incinerate the waste to produce electricity, which displaces green electricity, then yes, let's move it to Denmark. If we have a situation where that electricity is displacing fossil, then leave it there. So, summing up, mixed combustible waste may pollute future clean energy systems, either in Denmark or abroad, but if we have an equal level of low carbon energy systems, it's better to incinerate in Denmark where we can utilize the heat. The energy displaced, whether we import to the high elect or the low elect scenario in Denmark, has a higher impact on the balance than the quality of the imported waste. Then you saw that sustainability of biomass also have an impact. And, well, leaving the waste at an engineered landfill with a good subtraction of the landfill gas and a use for electricity production, where we also take into account that the carbon stays in the ground, may be a best option. But furthermore, I mean, it's a good idea to look into other environmental impacts. There may be other reasons to export than just the climate issue. So overall, is there a climate benefit of importing waste? Today, yes. In the future, not really necessarily. So basically, don't build excessive amounts of capacity in order to import waste for climate reasons. And only import waste if one, the alternative waste management will be at a sanitary landfill with poor landfill gas recovery, or if two, local incineration would displace green electricity, for example from Norway. Whoa, I just need a drink. Coming to the next example. Renewable gas production. This is work which I've mainly done with my PhD student Rasmus Bramstoft. It's work in progress, but Amalia has also been involved here, and so has Ida, and again we see Hans. So, what we've been looking at is renewable gas production. What we're expecting in the future, as I told you before, is a decrease in the consumption of gas, but maybe a decrease particularly within individual heating, and maybe an increase in transport. So we thought it was interesting to say which are the cheapest options for producing this renewable gas and liquid biofuels in the future, and which local biomasses will be feasible to utilize. And we come back to this figure again. You remember this was electricity and district heating. This was where we were. Now we expanded with the gas system and conversion technologies. And then we also needed to include liquid fuels because they're in competition with the gas to provide fuels for the transport sector. We modeled, you don't have to read all this, but it's just to show that it's a bit complicated, many different options of producing liquid fuels and gas. And zooming into how we did for biogas, you can see that we have different types of biomass which we can transport at different costs into a biogas plant. Then the biogas plant produces biogas which can either be used raw in an engine to provide electricity and heat, or we can upgrade it by removing CO2 and enter it into the gas grid, or we can have even more if we combine it with hydrogen from electrolysis, goes through a methanation process, and then we enter it into the gas grid as biomethane. Now results. Very interestingly, we see that we use around 26 million tons of manure to produce biogas, which is then upgraded by removing the CO2 to around 15 petajoules of biomethane if we have a price of around 15 euro per gigajoule for the biomethane. And we see that in order to provide around 50 petajoules of liquid transport fuel, we use 53 petajoules of straw and some refuse-derived fuel in a thermal gasification plant, and then together with hydrogen we have a production of methanol which supplies these 50 petajoule of liquid fuels, and we also have a district heating production to the grid because we have excess heat from the biorefineries. And then we looked at, well, what does it mean how high the gas price is in the base scenario. We had the 15 euro per gigajoule, then in a high gas price we have a 20 euro per gigajoule scenario. And what we see is that we have an increased use of biomass. We have wood waste that we are taking in and converting to syngas in a thermal gasification plant. And then we have additional hydrogen we add into the system in order to have a methanation of both the biogas and syngas to produce more renewable gas for the grid. So this small change in price is quite important. So the system is very sensitive to the gas prices that we will see in the future. And then we see that methanol plants were mainly placed in the east of the country, close to the bigger cities, in order to utilize this excess heat from the process, whereas the biogas plants were mainly placed in the west of the country, where the resource manure is. So concluding, which are the cheapest options for producing liquid biofuels and renewable gas? Well, thermal gasification of straw with subsequent conversion of liquid to liquid methanol. If this technology is available at the cost and efficiencies which my beloved colleagues in chemical engineering are telling us, then that seems very promising. Furthermore, anaerobic digestion of manure with subsequent CO2 removal and feeding into the gas grid with low gas prices, whereas additional wood waste, thermal gasification and methanation at high gas prices. So quite a change. And where should the plants be located? Well, this obviously depends on where is the resource and where can we also utilize this excess heat. Next steps, we're looking into improved modeling of the gas grid and storages in the Future Gas project. So, future development. Well, first of all, within the modeling, I think that there will come more interesting energy technologies we have to look at. Could be interesting to include learning curves and analysis of the different technology readiness level that the energy technologies have. We want to supply more policy analysis, work with our colleagues, economists. We want to look into uncertainty. We are currently working with it with the scenarios. As you saw, we're starting looking into global sensitivity analysis and Monte Carlo simulations. There's also the option of looking into stochastic programming and optimal control approaches. This is all in order to take into account that we don't really know how the future is going to look, and we have to look into this in kind of robust ways to give robust decision support for politicians, but also investors. We want to look into what does it really mean, how we are aggregating time and space, how important is it, and what does it mean for our results. We're doing that with our operation research colleagues. And then I think that apart from climate, I showed you today we've started looking into biomass sustainability and energy consumption abroad of products or alternative uses of fuels. And I think maybe water consumption and critical resources will be things we might need to look into in the future. So more work also with our LCA colleagues. Another issue is behavioral aspects. We've started looking into that a bit in the transport sector with modal choice and the travel time budget in the times model. But we're also bewildered by the fact that energy savings are so socioeconomically feasible, but they're not really happening, and we need people to tell us why not, because our models say it's very feasible. So the good news is we're going to have even more cross-disciplinary cooperation with all these brilliant colleagues around. And furthermore, it's very important to me that we improve on the dialogue. I think we should improve the access and transparency, promoting this dialogue. We should have even more interaction with society. We should have open source models, both on the data side, on the code, maybe also on the programs. We should provide online courses. We've started with Balmoral. Maybe we'll do it for Times, have an open course. And then I think we have to continue working with dialogue-based scenario tools. We're doing this with our small stream tool that many of my students will know. And we are also in the Comets project working with the dialogue-based scenario tool. You'll have to ask my PhD student about that. Well, if you want further information, please go to my homepage. Most interestingly, all the PhD projects are linked there, and there's these brilliant young people. First was Carsten Hedegaard, Christoffer Lytke Jørgensen, and then Ida Græsted Jensen, who all finished. And then we're still waiting for Amalia and Giada, Rasmus and Sarah to also finish their PhD journeys. But of course, this is some of my most important work, is working with these brilliant young people, and also one of my biggest privileges. Please go to our model homepage where we do supply open source models, and also check out we're working on commenting on the climate agreement with our models and saying what is really the impact of the initiatives that the government is suggesting. And of course I have an email address that you're all welcome to tell me your brilliant ideas in. Then I always say that working in this division is like working in a candy store. There's too much different goodies to choose between, and this is projects and it's courses, and it's super interesting and really difficult to choose. And of course, one of the reasons why it's so fun is all the brilliant people I'm working with. So thanks, before I forget it, to my PhD supervisors, both formal and informal. So Henrik Lund from Aalborg University, Thomas Astrup from Environmental, and our own Paul-Erik Morthorst was my formal supervisors, whereas I would say that Peter Meibom, sitting there in the audience, and Hans Ravn has been my informal supervisors. I have the best colleagues. So of course, this wouldn't be the same without them. I have brilliant cooperation partners in industry and in the authorities, making it very fun to work. I have such inspiring students. They ask amazing questions, which are sometimes very difficult to answer. Some of my former students are still hanging around and are here today. And of course, my wonderful family, without which all this would not be possible, and whose support I'm eternally grateful for. Thank you.